looking at root locus now. As I said, this is the next chunk of our course. Root locus is an important tool in our toolbox in control systems, and I think it's almost invariable that you will get a root locus question in the exam. So this is definitely one for to pay attention to. So let's look at root locus. First of all, we know about the characteristic equation because we looked at that when we dealt with transient response. So we know that the transient response of a system is governed by the roots of the characteristic equation, right? We know that because those roots of the characteristic equation become the coefficients of the exponential terms of the transient response. Right? So that's transient response aspect, not the steady state, but the transient response, the part that decays over time, or if it's unstable, it doesn't decay and it grows over time. That part is determined by the roots of the characteristic equation. So it's frequently necessary to analyze the variation in transient response because something changes in your system. And the most common thing that changes in your system are the gains in your system. There can be other things that change in your system, but the gains are the most common things to change. And that would be, like, for instance, a proportional gain in your controller, or it could be that you have a PID type controller and you're changing your proportional, integral, and derivative gains, or any one of the above, right? So when you're changing your gains, that's an important parameter that changes. As we go further in the course and we look at frequency response, which is after root locus, we'll come to that. But we also learn about a different type of controller, which is called a compensator. So a compensator is a way of implementing a control system that tries to neutralize certain dynamics in your plant by compensating for them. So if you can create a model of your system and you can identify, say, what the poles are or what the zeros are in your transfer function of the system that you've modeled, you can then say, okay, well, if I create a compensator, I'm going to create a compensator that sort of cancels out one of those poles or cancels out one of those zeros. So we're going to look at that in more detail, but you might then say, okay, the variation might then be in the location of that, how you design your compensators. You might change the design in your compensator, and that will have an impact on the overall behavior of the system. So we could use it for that as well. So we're looking at how does your characteristic equation change, and how does the transient response change as you're adjusting or changing something in your system, primarily adjusting the control system part of it, your control algorithm or your control parameters. Computation and display of individual time responses is cumbersome. So if you say, okay, I want to try 3 different values of gain, just using a proportional gain in my system, I'm going to try 3 values, and I want to plot the time response of each value. I want to find out what's the rise time, what's the peak overshoot, what's the time to that peak overshoot, what's the settling time. These standard sort of parameters or characteristics of our time response that we might be interested in. If I say, okay, I'm going to calculate it now for the first gain and then draw the response based on that, then I'm going to calculate it for the second one, draw another response, calculate it for the third one, draw another response, then that's a long-winded, cumbersome approach to determining how your gain affects your time response, right? So if you have to plot each plot and kind of infer from that, it's long-winded and cumbersome. So what we need is a graphical method that allows us to sort of infer the variation in the transient response from the method that we use, and that's where root locus comes in. It allows us to infer what the transient response of our system is going to be based on basically what's called the location of the closed loop roots on that locus. A locus is like a trajectory or the course of a movement, right, in a domain. And the domain in our case when we're dealing with root locus is the S-plane, the S domain. So we're dealing with our Laplace version or our Laplace representation of our system and of our transfer function, our transfer function of our system, our transfer function of our controller. We're dealing with the S domain, the Laplace representation. And so the root locus traces the movement of the closed loop roots in the S-plane as some parameter. That's open loop transfer function parameter, which is, like I said, usually gain is changed. So roots could be, they're on the S-plane, but roots, we've touched on this already, roots can be either, of course, real or complex, or they could have a real part and a complex part. So the S-plane also has a real part and a complex part, or a real dimension and a complex dimension. So basically what we're using for the root locus is an Argand diagram. The y-axis is our imaginary value, the x-axis is our real value. And so we're plotting the location of the closed loop roots as they move along a path on this S-plane, which is actually an Argand diagram, right? So we're drawing lines on an Argand diagram which are representing the movement of the closed loop roots to how the real part and the imaginary part changes as some parameter changes, usually gain, like I said. Now, the locus always moves from somewhere to somewhere, and a locus always starts at the open loop poles, not the closed loop. We're tracking the movement of the closed loop roots, but we start with the open loop poles. And the loci, or the closed loop roots, move from the open loop poles, and they move either to an open loop 0, which is eventually the end point of that locus. It's like a line that goes from a pole to a 0. Or if there are, no zeros or more poles than there are zeros, then that open loop, the closed loop roots will, the locus of the closed loop roots will go to infinity. So there's two possible destinations for our closed loop roots. They're either, having started at a pole, an open loop pole, they either end up at an open loop 0, or they end up going off to infinity. And when they go off to infinity, they go off at a certain angle. We're thinking about an Argand diagram. They go off at a certain angle into space, if you like. So I'm just giving you a verbal description, and we'll go and look at some graphical sort of imagery, some graphics to help you understand it in a bit. Let's explain the concept of poles and zeros and make sure we all fully get what those are. So a 0 is a value of S which reduces the transfer function to 0, or in other words, a root of the numerator. If I draw an example block diagram here, it's a closed loop system. Our input is RS, we have negative unity feedback, our output is CS. So what is the open loop transfer function? So we could call it G, subscript open loop of S is going to be, go around the loop, right? So our open loop transfer function is going to be K times our plant. In fact, if I draw on this line with some feedback H, there's a transfer function on the feedback loop, then it would actually be K times the plant times H. If we call the plant G, then our open loop transfer function is KGH. So in this case, we're saying H is 1, so we don't have to worry about that. So we're going to say it's going to be K times S plus 3 over S plus 1 times S plus 2. So the zeros, do we have any zeros? do we have any values of S which will cause the overall open loop transfer function to reduce to 0? Well, yes, we do, because we say if S equals -3, then our open loop transfer function is going to be k times -3 plus 3 over -3 plus 1 and -3 plus 2 equals 0, because -3 plus 3 is 0 on the numerator, so the overall value of the transfer function is 0. So we have a 0, so S equals -3, this is a 0. A pole, and we're talking here again about open loop pole. Right? So we're looking at the same open loop transfer function that we mentioned before. An open loop pole is defined as the value of S which sends the transfer function to infinity, or in other words, a value of S that causes the denominator to equal 0, a root of the denominator. We can say if S equals -1, then our open loop transfer function is going to be equal to k times -1 minus 3 over -1 plus 1 minus 3 minus 1 plus 2, which of course is going to be minus 4k upon 0, because -1 plus 1 is 0 equals infinity. So, and then you could also say if S equals -2, it's going to be the same thing. It's going to be infinity, because that time this factor will reduce to 0, and our overall transfer function will have a 0 denominator, therefore this value will be infinity. In each case, these can either be written as real or complex. So both the examples here are real roots, but they could be real or they could be complex. And so let's have a look at another example here. What are the poles and zeros of this transfer function? If S equals -2, that implies g of S equals 0. Therefore, there is a 0, and we could even specify it's a real 0 at S equals -2. And then for the denominator, if we're talking about our poles, well, for a start, what's the order of the denominator here? The highest power of S would be S to the 4, so it's a 4th order denominator. What's the type of the denominator? Type 1, that's right. Okay, so, well, it's not just the type of the denominator, it has to be the type of the transfer function, because it has one pure integrator. Right, so having said that, what are the values of our poles? What values of S set the denominator to 0 and therefore set the transfer function to infinity? Right, so I can say if S equals 0, then certainly GS equals infinity, because this going to 0 would set the denominator to be 0, right? And therefore there is a real pole at S equals 0. We can also say, as Mikhail said, S equals -1, because that would mean that this term here goes to 0, right? So that means that the denominator would be 0 and GS would be infinite. We could say, therefore, there is a real pole at s equals -1. But what else? If s equals what else, what would the other denominator, the other roots be? The denominator, and Giovanna said it's -1 plus I or -1 minus I. Excellent. So if s equals -1, let's say plus or minus j, I'm going to use j, then those are the roots that would send this quadratic, because those are the complex roots of this quadratic, that would send this quadratic to 0. Therefore, you know, same story. Our transfer function is infinity. So we could say there are a pair of imaginary roots at s equals -1 plus or minus j. Very good. So we got our poles and we got our zeros there for this particular system. So now we're going to plot those poles and zeros on an Argand diagram. This is just an Argand diagram, and just by way of recap, as it shows here, any value on your Argand diagram Z is going to be x real plus y imaginary. So you come along x and then you go up y to get your complex number location, or your coordinate of your complex number. Now in our case, we're going to scratch it out and say S, because this is the S-plane for us. So we're dealing with the S-plane. So I can't delete that, so I'm just going to leave it there. But what we did say from the previous slide is that we have a real 0 at -2, poles at 0 and -1, and then imaginary roots or poles. I should actually change this to imaginary poles. Okay. At -1 plus or minus j. So let's plot those, if I can remember them, on the next slide. So we have a, I'm going to draw poles as x's and or x's and zeros as circles. And in fact, just to make it even clearer, let me use different colors. So I think I'll use green actually for my poles, and I'll use red for my zeros. So I have poles at 0. I'm going to say this is -1. Let's call this -1, 1, 2, -2, 1, 2, -1, -2. So where else do I have my poles? I have one, we said, at 1, and then we have another pole at -1 plus j, another pole at -1 minus j. So those are the locations of my 4 poles, and we said we have 1, 0 at -2. And so I've just plotted the location on an Argand diagram of these poles and zeros that we identified here. Okay, or here. Right, so that's how we plot our poles and zeros. Remember, they are open loop transfer function that we use to find our poles and zeros. So our poles and zeros are always open loop. So let's determine for this next example here, the open loop poles and zeros. Let's determine the closed loop roots. Now, this is moving on one stage, because we're not just looking at what we did before, which is find the open loop poles and zeros, but now we actually want to determine the closed loop roots for varying values of k. So our amplifier k, or our controller here, we're changing that creating different values of k, and for each value of k, we want to determine what's the location of our closed loop roots. So our open loop transfer function will be used for determining our open loop poles and zeros, which is g equals k, well, let's say GOL equals KGH, right? Our closed loop transfer function will be used to determine our location of our closed loop roots, which will be a forward path, which is KG over, we're calling this G here, right, just for shorthand's sake. So our closed loop transfer function is our forward path over 1 plus our open loop. So we'll find the roots of this, get the closed loop roots of this and look for the various values of k, right? And you can see k is a factor on the denominator. Now remember, our closed loop roots are actually, well, say remember, but just to underscore, the closed loop roots are actually the roots or of this denominator of the closed loop transfer function, and they are and that is also, remember, 1 plus kgh equals 0 is our characteristic equation. So we have linked the closed loop roots and the movement of the closed loop roots to the change in our characteristic equation as k changes. And then what we want to do is actually plot those open loop poles and zeros. Well, we could see by observation there are no zeros on the open loop transfer function for this particular one. So we're going to plot those open loop poles and the closed loop roots that we just found here. We're going to plot them in an Argand diagram. We're going to join the dots, and when we join the dots, that's going to give us our root locus. So first up, let's look at, I've just shrunk everything down, so we've got some working room here. So first of all, let's determine our open loop poles. We already said there are no zeros because there's no denominator on our transfer function there. So our open loop poles, it's very easy. We could just do it by observation. KGH equals, well, this is our open loop transfer function, GOL equals KGH equals K over S plus 1 times S plus 4. Therefore, we can see immediately that we only have two poles, one at -1 and one at -4. So I could draw those on. Now, I use my same convention. I think this time, let me draw a scale on this chart first. One thing very important when you're plotting root locus plots or using your Argand diagram for your S-plane, you always have to match the magnitude of the scale on the X and the Y axis, or the imaginary and the real axis. So I use one block per unit on the real axis, on the x-axis, and I'm using one block per unit on the imaginary axis. And those always have to match for reasons we'll come to later. Right, so our poles are going to be at green for poles, so green x's, one at -1, one at -4. There are no zeros, so that's it. So next we're going to move on to determining this one. So we've done this. Next we're looking at this. Determine our closed loop roots for various values of k. So first of all, we need to get our closed loop transfer function, and that's going to be forward path over 1 plus open loop. So our forward path is k over s plus 1, s plus 4, and our open loop is the same because we have unity feedback. Our feedback loop has no transfer function on it, so that means our open loop and our forward path are actually the same in this case. Right, so if we multiply that out, then whenever we change k, we actually change the location of the roots of the denominator of our closed loop transfer function. So we're moving our closed loop roots when we change k. So for k equals 0, s equals minus b plus or minus root b squared minus 4ac over 2a, which is minus 5 upon 2 plus or minus 25 minus 4 times 5, which is 20, all over 2. Right? So that's going to be minus 2.5 plus or minus 5 root 5 upon 2 minus 1.38, and we have minus 3.6. Right, so that's it. Minus 1.4 and minus 3.6. So I'm going to plot those points. And minus 3.6 is about here. Right, and those correspond to k equals 0, right? So if we continue with that for different values of k, k equals 1, k equals 2.25, etc., then we're going to end up with a number of points on a line. So to save some time, I'm going to give you the answer. What you'll find is you'll have, for k equals minus 1, you have a point somewhere here. So these aren't precise values, these are just approximations. For k equals 2.25, you'll have both your values at minus 2.5. For k equals 4, you're going to have a value of minus 2.5 real, but then it's going to have an imaginary part as well. And the imaginary part is going to be about 1 point something, plus or minus 1 point something. So you see that you have a value and you have a conjugate, a complex conjugate. This is important information for you. 8 might go up to about here, right? So you have a complex conjugate as well. So what we discover is that the roots move along a line and then they diverge, and one closed loop root goes upwards, the other starts from the pole, will come along the real axis, then diverge from the real axis and have a complex part and go down to a negative value, negative imaginary value. So what we see here is that for certain values of k, then you're going to have purely real roots on the real axis. Once you get above a certain value of k, which in this case is 2.25, that's like a critical value of k, then it's going to deviate, the closed loop roots will deviate and they'll shoot off in this case a plus and minus direction. These are supposed to be straight, right? And you'll get a reflected value within a positive imaginary part and a negative imaginary part. You're always going to have that complex conjugate. So that means that you actually only really need to plot, one half plane on the imaginary axis, because you're always going to have symmetry of the imaginary along the real axis. because you're always going to have the complex conjugate. So in fact, we don't necessarily need to plot the negative imaginary axis. You could just, the negative imaginary values, you could just plot positive imaginary values, because you're always going to have a value in its complex conjugate. All right? So we're seeing how the closed loop roots move in the S-plane based on the value of a parameter. In this case, we're changing the value of our gain K in our amplifier. We're also seeing that they start off being real, but then they become imaginary. The difference between a real root, closed loop root, and an imaginary closed loop root is that an imaginary closed loop root will have an oscillatory component to it. So as soon as you start to move your closed loop roots come off the real axis and they have an imaginary part to them, then what you're saying is that the transient response is going to have some oscillation in it. Instead of just being, if we look at a step response, instead of the step response just, if this is our step input, kind of going like this, now as soon as it departs, the closed loop root moves off the real axis, you're going to have some level of oscillation in your response. And that's going to start very small, but as you get up here, then that amount of oscillation is going to grow, and you're going to have more oscillation, right? So there's a relationship between the time response, that you get, the transient time response, and the location of the closed loop roots on the S-plane. And that's really kind of at the crux of what we do with our root locus. Because once we can establish what the relationship is between the location in the S-plane of a closed loop root and the time response, then you can kind of go straight from this to that. And this closed loop root location is going to tell you what kind of time response you're getting. So that's what we're working towards here. And so just to continue along that trajectory of explanation, let's look at a simpler system now. It also has unity feedback, but it just has a first order system. So that means what? Well, when we look for our poles, we're only going to have one pole, because we only have a first order system. And not only are we only going to have, anytime you only have one pole, then you only have one locus, because you have the same number of loci as you do poles. So if you have 10 poles in the 10th order system, you have 10 loci. If you have 4 poles, you have 4 loci. 3 poles, 3 loci. Third order system, 3 poles, 3 loci. Second order system, 2 poles, 2 loci. Right? So let's look first of all. Well, we could instantly by observation say we have a pole at s equals -3. Right? We don't need to do any calculations to see that immediately with this, because our open loop transfer function is going to be this k over s plus 3, and it's unity feedback, right? So we instantly say a pole at s equals -3. So let's move to our closed loop transfer function. So this is our GCL, which is our closed loop transfer function, equals our output over our input. So there's forward path over 1 plus open loop again, right? Forward path over 1 plus open loop. So multiply that out, we get S plus 3 plus K, right? So now we're going to, again, for a simpler system than the one we just looked at, we're going to look at what happens as K varies. And as K varies, we can see that the location of our closed loop is also going, our closed loop root is going to change as K varies, right? So it's going to start off with K equals 0, it's going to be at -3 at the pole. As K increases, then it's going to move away from that location. So here we go. We've got 3 values of K. K equals A, K equals B, and K equals C. So these ones, K is increasing in each case. So because as K increases, you get a larger negative value of S. So A is smaller than B, B is smaller than C, K is increasing. So as we're increasing K, what we're doing is we're taking our closed loop route from our pole away towards infinity, right? There's no zero, so this locus is just going to go off into space, going to go off into infinity. So as we are increasing our value of k, we're also changing our time response. This is our time response, and you can see that the increase in k reduces our steady state error. It's a unit step response, but the maximum value of this graph is 0.8. So we can see we're not getting to our step response because our input would be 1, right, up here somewhere. But we're not getting up there. With a low value of k, we're falling very far short. We just have an output of about 0.15. As we're increasing, we're getting a higher output. Increasing, we're getting to about 0.5 by the time k equals c. And in this case, k is going to be about 3.5. Right. But you'd have to, keep increasing k and keep increasing k to reduce the steady state error. But you notice, apart from the steady state error part of it, which we're seeing here, for k equals c, for instance, you're also seeing that as your k increases, the time response is accelerating. The rise time is reducing. You're getting up to a higher value more quickly. Right? With this one, this is about somewhere around here. You're still reaching your final value, and that's slightly shifting as you're getting to higher values of k. So you get a faster rise time and a slightly faster convergence to your final value. So this simple example showed us quite a few things. First of all, when k equals 0, the closed loop route is located at the open loop pole, and that's generally true. As k increases, the closed loop route moves away from the pole as values of k increase. And as k increases, the transient response decays more rapidly, and thus the steady state is achieved more quickly. So here are 3 things that we've learned by just looking at the most simple case of a closed loop first order system. The first thing we have to do when we're plotting the root locus is that we have to take the open loop transfer function, and then we get the open loop poles and the open loop zeros. We have to find those. So what's the open loop transfer function? We can call that GOL, and that will be, as the arrow shows, k times 1 over s into s plus 1, s plus 2. So what are our poles and zeros? Well, this one's very easy. It's going to have poles at s equals 0, minus 1, and minus 2. And the zeros, none. Okay, number of separate loci is equal. How many loci are there is equal to the number of open loop poles. Right? So, and each loci will end either at the pole, at the zeros, or infinity. So in this case, how many poles do we have? That is 3 poles, no zeros. Therefore, each pole will end at infinity along an asymptote. Loci are symmetrical about the real axis. We covered that last time as well. We said that you basically just have to plot one half plane, the positive half plane, and that's enough. I just did this, create the open loop transfer function, find the open loop poles, open loop zeros, there are none. Then we start to create or sketch the root loci on the real axis. So here I've drawn a real axis. It's a simple one, a little stubby imaginary axis, and then a long real axis, because we know our poles are only real. So we have, in this case again, it's only real poles. So all three of these poles are going to be on the real axis. So for the purposes of this bit, I just need the real axis really. Right, so first of all, let me plot my poles. I've got one at 0, one at -1, one at -2. So there's the one at 0, -1, -2, and I'm plotting them all as x's, and I'm using green just because, right? And then I plot my zeros, but I don't have any. So there are no zeros to plot. And then what I have to do is create the locus that lies on the real axis. Right, so to do this, what I'm going to do is I'm going to start at my right-hand side to the right of any poles or zeros. So I'm going to start on my right-hand side, end of the positive real axis. And then I'm tracking basically, I'm kind of going backwards from this end, and I'm going in this direction. And as I track, whenever I cross or interact with or intersect a pole or a zero, it toggles the real axis. So let me demonstrate to you. I'm coming from the right back towards it. When I hit this real axis, this pole at 0, at that point I pick up the locus, and the locus will continue along the real axis until I get to another pole or a 0. So I know that there's a real axis, there's a locus lying on the real axis between these two poles. When I get to the second pole, it turns off the real axis. So it basically toggles on, off. As you're going along the real axis in a negative real direction, you keep toggling on and off every time you intersect either a pole or a 0 on the real axis. So I keep going, there's no locus on this section at all. And then when I get to this pole, I pick up the locus again, and it continues along the real axis and off to infinity. If I stand at any point, if I imagine I'm standing on the real axis here and looking this way, if I see an odd number of poles or zeros on the real axis, so I'm standing on the locus. If I'm seeing an even number, then I'm off the locus. All right, so if I move across here, if I walk across to this point, and I'm looking this way, I'm seeing 1, 2. So I'm seeing an even number of poles or zeros to my, in the positive real direction. So therefore, I'm off the locus. If I walk further this way, and I stand here, I'm looking in this direction, I'm seeing 1, 2, 3 poles on the real axis. Therefore, it's an odd number, and I'm on the locus, and indeed I am on the locus, right? So that's a way, it's just a kind of trick I teach students to figure out where the locus lies on the real axis. So we can plot locus on this section, locus on this section. You notice here I said sketch. So sometimes I'll ask you to plot the root locus, other times I ask you to sketch the root locus. If I ask you to sketch, you don't necessarily need to use graph paper. But if I say plot the root locus, that means I expect a precise drawing using graph paper. That's just a little distinction there when I ask you to sketch or to plot. So the next thing we're going to do is we're going to derive the asymptotes of the root loci. Now, notice this has only real poles. It's got 3 poles. There are 3 of them. And how many zeros? No zeros. So that means that each of these poles produces a locus, and that locus goes off to infinity because there are no zeros to sort of absorb the locus. That means this locus coming out of here, out of this first pole, has to go to infinity. That means that this pole is also producing a locus coming out of it, and that locus has to go to infinity. This pole is producing a locus. That locus has to go off to infinity. What that tells us is a couple of things. Number one, these two loci, they're looking like one solid line, but in fact it's one line from each pole, and at some point they intersect and they have to come off the real axis. Right? So they'll actually depart from the real axis at some point, and the locus will go off towards infinity. This one, one up and one down in the negative direction. And as I said, they're symmetrical about the real axis. So what we want to do is find out, well, what are the asymptotes of the root loci? Because these loci that I've just sketched here, they'll always go off to along an asymptote. They'll be asymptotic. So how do we determine the asymptotes? Because we create straight lines, and the loci are going to converge to those straight asymptotic lines. And those asymptotic lines all emerge from a single point on the real axis. So we have to find the center of the asymptotes, which is the point on the real axis from which those asymptotes emerge. And then we have to find the angle of the asymptotes, which are the angles of the straight lines that emerge from that single point on the real axis. So the branches of a root locus approach a set of straight line asymptotes at a large distance from the origin. The asymptotes emanate from a point on the real axis called the center of the asymptotes. And to get the center of the asymptotes, sigma c, we sum the value of all the poles and then subtract the value of all the zeros, and we divide that by the number of poles minus the number of zeros. Right? So we sum between 1 and n, where there are n poles. We sum between 1 and m for mummy, where there are m mummy zeros. Okay, and then we subtract the number of zeros from the number of poles. That gives us a number, a numerical value, which is the center of the asymptote. So in this case, our poles are at 0, minus 1, and minus 2. So we sum them together. Of course, minus 1 minus is minus 3, right? Minus 0, because there are no zeros, divided by 3 poles, n, minus no zeros, m. So that's minus 3 from these 3 upon 3 equals 1. Sorry, minus 1. Right? So we have a minus 1. That's the center of our asymptotes for this particular root loci. They're going up to the previous page. That means this location right here. This would be the center of our asymptotes. And straight lines emerge from that point and go off in different directions. What the angle of those asymptotes are, or the angles are, that's what we have to determine next. So let's look at the angle. The angle made between the asymptotes and the real axis is given by this. Theta equals 1 plus 2k times pi over n minus m. Right? So our k goes from 0, and it's an integer value, and the number of values of k that we use equals the number of n minus m, right? The number of poles minus the number of zeros. So in this case, n minus m equals 3, because there are 3 asymptotes, so we use 1, we get 1 value of k per asymptote. So we use this one, and this one. So for our 3 poles and no zeros, we'd use values of k of 0, 1, and 2. So what would our theta be in this case? Theta equals 1 plus 2k, and so you get a value for each value of k times pi over 3. So when k equals 0, which is the first value of k for which we assess theta, theta is going to be, as you can see from here, this goes to 0, so it's just going to be pi over 3. When k equals 1, theta equals, well, now it's going to be 1 plus 2, which is 3 pi upon 3, which is just pi. And then when k equals 2, theta is going to be 1 plus 2 times 2, which is 4. So that's 5 pi upon 3. So you can see the values I just derived there. They're the same as these values I put here. All right, just to make sure we see that. We use 3 values of k, 0, 1, and 2. If we had a higher, say we had a value, if we had let's say 6 poles and 2 zeros. If we had 6 poles in this system and 2 zeros, then our n minus m, in that case, 6 poles, 2 zeros, we'd have 4. So in that case, we would use values of k of 0, 1, and 1, 2, and 3, because we use 4 values of k. K is always fixed. It's always 0, 1, 2, 3, etc. Right? So k is always fixed at 0, 1, 2, 3, 4. It keeps incrementing up. It's just an integer. Right? And it depends entirely on the value, on the number of asymptotes. So we could say we use 1 value of k per asymptote. How many asymptotes do we have? We have 3 asymptotes because we've got 3 poles producing loci and no zeros which are absorbing loci. Therefore, we're going to have 3 poles going off to infinity along asymptotes. So we've got 3 asymptotes for this system. We're going to have 1 value of k per asymptote. So we're going to use values of k that are 0, 1, and 2. Those are the first 3 values of k. Substitute them into this equation. So you're going to have theta 1, as I showed it here. This is theta 1, this is theta 2, and this is theta 3. We've got theta 1, theta 2, theta 3. The next thing we have to do, now we've got our asymptotes defined, our center of our asymptotes. We have to find a breakaway point. Now, I did indicate here these loci, one is coming out of this pole, one is coming out of this pole. They have to meet somewhere in the middle, and at that point they have to depart from the real axis. One of them will go up, one of them will go down, and then they'll converge to the asymptotes that we've just sort of calculated. So there's going to be a breakaway point where that happens, and the breakaway point sigma b is where 2 or more branches of the loci depart from or arrive at the real axis. All right, so we want to find this point right here now, where that departure takes place. Okay, it's called the breakout point or the breakaway point. To get this, the breakaway point occurs at in a mathematical condition where the change in k with s equals 0, dk by ds equals 0. And that might seem strange, but basically remember that the loci, the root locus, shows the movement of the closed loop roots as you vary a parameter, which is usually gain k. Right? So as you're changing your value of your gain, those closed loop roots are moving. And the breakaway point is basically a point of inflection in the relationship between the change in k and s. So that's why we use this condition that the derivative, the first derivative k with respect to s equals 0. That's an inflection point in k by s, right? So that's the condition that we're trying to identify. We know 1 plus k g h equals 0 is our characteristic equation, and it is the roots of the characteristic equation that we're concerned with, right? So we can rearrange that to say k equals minus 1 upon GH. You've just taken, you know, the one across and then divided by GH to get the value for K. So in this case, we form our characteristic equation, 1 plus KGH, right? And then if we multiply that out, multiply our characteristic equation out, then we get a polynomial in S with the constant K. Now, if we differentiate with respect to S, then this differentiates to 3s squared. This differentiates to 6s. This differentiates to 2. And this one, well, you just differentiate it to dk by ds equals 0. We've also already identified that the point of the breakaway point occurs when dk by ds equals 0. So that means we can set this to 0, and we're left with 3s squared plus 6s plus 2 equals 0. And then we can find the roots of that, and those roots will be the value. It should be a real value. That'll be the value at which that breakout point takes place. So let me remove some of this annotation so you can see the slide. All right, so I got this 3. We differentiated our characteristic equation to get this 3s squared plus 6s plus 2 plus dk by ds, and then we set dk by ds equals 0. Then we could just use our quadratic root equation to get the values, 2 values of s. One is minus 0.42, the other is minus 1.58. 0.42, so this one is on the locus, but minus 1.58. That one is here somewhere, so it's off the locus. So that is not a good result, but this one tells us where our breakout point is. This is the open loop transfer function we're looking at now. GS equals K to S plus 6 over S into S plus 4. So for this one, we have poles at 0 and minus 4, right? And we got a 0 at minus 6. So if I plot that as I've done using MATLAB, you'll see there's a pole at 0 on the real axis, a pole at minus 4 on the real axis, and a 0 at minus 6. So we have 2 poles and 1 0 in this case. When we determine how many asymptotes there are, we're going to have 2 poles and 1 0, so there's going to be 1 asymptote. Right? But you can see that these 2 poles, when we plot the locus on the real axis, we start from the left-hand side, come along, we're going to pick up locus here. At this pole, the locus is going to run along the real axis. To the next pole, then we have no locus between minus 4 and minus 6. At minus 6 at the 0 now, we pick up a locus again, and it runs along and goes off to infinity. So we actually plot the locus that lies on the real axis like that. But these 2 poles, you know, the loci coming from each one, and it's nice with this plot, you can see from MATLAB it shows one in blue and one in green, so you can see which is which. So the one coming from the pole at 0 goes down and breaks off the real axis and goes down, and the one coming from minus 4 breaks off the real axis and goes up. Now, because there's only one asymptote, that asymptote is going to be at minus 180 degrees, going off on the real axis in a negative direction. So that means this locus has to come around and go back to here. And then what's going to happen actually is that one of these is going to go to the 0, the other is going to go off to minus infinity. So it creates this circle. So now we see that since there's this one asymptote, then the loci must diverge. They diverge here, but then they reconverge onto the real axis. They swing back round to the real axis and converge onto the real axis, or break into the real axis here. One goes back to the 0, the other goes off to minus infinity. So if we did the same thing and use the characteristic equation here, we would find that we're going to get two values. So our characteristic equation would be 1 plus kg h equals 0. So that's going to be 1 plus k 6 plus s over s plus 4 equals 0. Now this one's going to end up being a bit more complex. So we're going to get s squared and 4s and ks and 6k equals 0. So we're going to end up with s squared and 4 plus k s and 6k equals 0. Right, so now we can't just differentiate and set dk by ds equals 0 because we've got an implicit k here. Right, so what we have to do, we'll come to this in a bit, we have to do a different approach, probably combine the k's and set k equals something and then do it that way, or we could do implicit differentiation, which is a bit more tricky. But if we solve this, just sort of cutting a long story short, if we find the roots of this equation and set dk by ds equals 0, then you're going to get two values that are on the real axis. But when we get two values that both lie on the real axis, we know one is a departure value and one is a convergence value. So we're just building up how to plot different types of root locus using the rules that we're learning. Okay, so we've got a breakaway point here. The loci goes around like this, as the arrows show. You have a break-in point, and then the loci go like this, one to the 0 and the other to infinity. Next, we're going to find the point where the loci cross the imaginary axis. And so let's deal with this one now. I'm just going through, I'm giving you all the steps for plotting the locus, then we'll practice it and you'll get plenty of practice both by going through the tutorials and going through the past papers and so on. Let's find the value of k for marginal stability and omega c, which is the critical natural frequency. But that also gives us, finding omega c, also gives us the intersection of the root locus with the imaginary axis. Right, so that value, omega c, that's the intersection between the root locus and the imaginary axis. And we've already have a method in our toolkit for finding the value of this marginally stable or value of k gain that gives us this marginal stability and a value of the corresponding natural frequency. We did that when we dealt with the Routh-Hurwitz stability criterion. So taking the characteristic equation of this particular system that we're analyzing here, the system here, open loop transfer function here, that we're analyzing right now. Okay, so taking this system, then go to 61. All right, this is the characteristic equation. We already derived that. So that means we can now create our Routh-Hurwitz array. So we've got s cubed term, we put our powers of s down the left-hand side, and then we create a matrix from that. And the first term is the power, is the coefficient of the power in s. Then we skip a term and put down the n minus 1th power of s coefficient, so that's 2. And then next row, we go to s squared and k. Then we form the determinant. So when we multiply this out here, cross multiply, then we end up with 6 minus k because of the negative. Right? So 6 minus k over 3, but the criteria for marginal stability is that in that case k has to be less than 6. If k goes above 6, this term will become negative, and then you'll have a change of sign in the first column of the Routh-Hurwitz array. And that's the criteria that tells you the system's unstable. So when k equals 6, you get a 0 here, and in that situation, the system is marginally stable. And that's what we're looking for. We're actually looking in this bit of analysis for a system, the value or the behavior of the system when it's in marginal stability. So stability is between the values of k of 0 and 6, but we also learned before that we can form what's called the auxiliary equation from the s squared row of the Routh-Hurwitz array. And the auxiliary equation then will basically just be this row here. Extract this row. And that gives us 3s squared plus a constant k equals 0. Right, that's our auxiliary equation. When we set k equals 6, that's the critical value, then we get a value of s of plus or minus j root 2. Yeah, so s squared equals minus 6 upon 3, and that implies s equals, that's 2, that's minus 2, square root of minus 2 is complex, j root 2, plus or minus. Right, so that's a value of s for marginal stability, and that also, we learned before, corresponds to your critical frequency. So that's the frequency of oscillation of your system when it's in that critical or marginally stable condition. The frequency is actually root 2 radians per second. That's the frequency of oscillation. Now, this corresponds directly to a situation which is like a second order system that's marginally damped, and we did look at that before as well. If we have the prototype second order system, if zeta equals 0, that means you have no damping. That means this term goes to 0. So in that case, a system which is in marginal stability, there's no damping, so it's just going to oscillate forever. Omega n squared over s squared plus omega n squared. All right, so this is our sort of marginally stable condition, and you can see it's oscillating at omega n squared. The roots of this are at s equals plus or minus omega n, and we're calling that now for this condition omega c, which is the critical natural frequency when the system's completely undamped. Because you also have a natural frequency when it's damped, but this is when it's undamped. We call that the critical natural frequency. Right? So the roots of that denominator are omega n. So that means that if we're plotting the roots of our characteristic equation when the system is completely undamped, that's the point where your closed loop roots cross the imaginary axis. At this point, we could say when closed loop roots cross, remember the closed loop roots are moving from your poles, and as k increases, they're moving out of your poles, and then they're moving towards a 0. We don't have any in this particular example, or they're moving to infinity. So they're moving off along the asymptote, one going up here, the other going down here, right? And this one departing from -2 and heading off along the negative real axis. But these two here, both of them are symmetrical about the real axis. One of them is progressing, and it will get to a point where, as the gain increases, this locus is going to, the closed loop root location is going to lie right on the imaginary axis. So when the closed loop roots cross this imaginary axis, then at this condition there's no real part in the closed loop root, the system will oscillate in what? Simple harmonic motion at omega c radians per second, and in this case omega c equals root 2. In fact, it technically equals plus or minus root 2 because you have one value here and it also crosses, the other asymptote crosses at minus root 2. So that's important to understand, that the point where the closed loop roots are running along the locus cross that imaginary axis, there's no real part, so that means that the magnitude of the response is not decreasing, because the exponential won't have a decreasing negative real part in the closed loop root. It's not increasing either, because it doesn't have a positive real part in the closed loop root. But you know, as k continues to increase from this point, it's going to go here, and once it crosses over this imaginary axis, it's going to become unstable, because now the closed loop root has a positive real part. That means that that exponential coefficient, exponential power, is going to have a positive value, and that means it's going to grow to infinity over time. So I want to talk next about dominant poles. It should actually be dominant closed loop roots. So the transient response of a system may be equated to a sum of exponential terms. We've dealt with this already, and the contribution of each term is determined by the roots of the characteristic equation, one of the roots of the characteristic equation. The terms are not equal. Some roots are more important than the others and dominate the response. So if we have this closed loop transfer function here, the roots of this, the closed loop roots of this closed loop transfer function, this one is going to be minus 8. This one is going to give us minus 4. And this one is going to give us minus 1.5 plus or minus 4.2j. We have a fourth order function, so we've got 4 closed loop roots. These are the values of the positions of the roots here. Okay, this one of course is complex. So these two are both on the real axis, minus 8 and minus 4, but this one is complex, and it will give a sinusoidal type of output, sinusoidal response, and those roots will correspond to the output function AE to the minus 8t, and BE to the minus 4t, and CE to the minus 1.5, let's do it this way, minus 1.5 plus or minus J 4.2. All right, and that could also be written as A e to the minus 8t plus e to the minus B e to the minus 4t plus C plus C e to the minus 1.5t sine 4.2t plus phi, right? So we've basically just taken the imaginary part, which is sinusoidal, and we've written it in the sinusoidal form instead. All right. So if we were to plot the behavior of each of these parts, what's going to happen? Well, I think I've done it better on the next slide. You can plot the output y against t, and the first one, so I'm doing a light green, is going to decay very quickly because it has a high exponential coefficient or exponential power of minus 8t. So this one's going to come down like this, right? The next one, so I'm going to do in orange, it's got -40, so that one's going to come something not like that, more like this. It's going to decay a lot more slowly. This one has -1.5 T, but it's sinusoidal. So this one we're going to do in purple. And this one I'm going to split it into two parts. I'm going to do the envelope -1.5 T, right? So that's going to be plus or minuses on the negative side as well, which I've not got space for, but understanding that this is going to go both ways, right? And then it's got a 4.2 frequency sinusoid, so it's going to come something like, it's probably something like this. Right, so pretty rough sketch, but you get the general idea. So in the overall response, when you add up the different elements, these are added up, right? Green, orange, purple, they're added up. And the green one is going to have obviously an effect in this first little section. Let's say between about here and here, it's going to have some effect, but after that it has no effect. It basically is eliminated. Mr. Orangey, that one's going to have some effect probably to about here, in this range. After that, pretty much no effect. But purple will continue. For a start, it's going to have the most significant impact on the overall response because of the oscillation, but then it's going to continue much longer than the others to have some impact. So you can say purple, the sinusoidal part, that closed loop roots that correspond to that part is going to dominate the response. They're going to be more important, they're going to last for longer, and they're going to have a higher value because the coefficient of that exponential decays the most slowly. Well, that exponential term decays the most slowly, rather. Right? So those closed loop roots correspond to poles or closed loop roots shown on this root locus. So you can see these are purple from the previous slide. This is our orange, -4, and this is our light green, -8. Right? So you can see that the dominant closed loop roots, the purple ones, those ones are the ones closest to the imaginary axis. So, and then I've kind of got a slightly better plot of the time of the transient response than I had on my rough hand sketch before. Right? So you can see how these things decay. It's not even a very accurate sketch, that one is just rough. But we can see the total response is dominated by this decaying sinusoidal because those roots are much closer to the imaginary axis, the purple roots, right? Now flashing red. And since the dominating roots are second order, so yeah, you do still get some effect from the orange and the green, but the purple, flashing red ones, those ones, basically if you were to take it, you could approximate the system to being second order because those roots are the most important in the response. So we could say that since the dominating response, some dominating roots are those second order ones, the system can be approximated to an equivalent second order system. And this gives us a nice system with a well-documented time response, right? Because if we're dealing with a second order system, then we can express the behavior of that system in terms of a damping ratio and natural frequency. And we're very familiar now, we're getting familiar with the concept of a damping ratio and a natural frequency to describe the system and what that means, in terms of we're about to look at how the damping ratio and natural frequency correspond to the position of those dominant second order roots. So we have a higher order system, we're dealing with a fourth order system, but it's been reduced to a second order approximation, making it possible then to use that second order system's data reasonably well. to affect a successful design. It's not going to be precise. You're going to still get some variability, but you can use it reasonably well. Let's consider a normalized form of the second order transfer function. So we've now taken our fourth order system, we're approximating it down and saying those second order roots are the ones that are dominating. And because it's second order, we're going to approximate the system to being a second order transfer function. We have a standard or normalized form of our second order transfer function. It looks like this. We've dealt with this before. All right, now, what are the roots of this second order transfer function? The poles, and they would be at the value of s equals minus b plus or minus root b squared minus 4ac. So s equals minus 2 zeta omega n plus or minus square root of 4 zeta squared omega n squared minus 4 omega n squared, right? And all of that over 2. We can cancel the 2's here for the real part. So we've got minus omega zeta omega n plus or minus root 4 times omega n squared into zeta squared minus 1. That's still going to be over 2, that part. We cancel the 2's on the real part. All right, so this is going to give us minus zeta omega n. Then that 4, when you take the square root of it, becomes 2. The 2's cancel. So we're just going to end up with plus or minus omega n root zeta squared minus 1. Now I'm going to do a little trick, and I'm going to make this a negative inside here. And instead of zeta squared minus 1, we're going to do 1 minus zeta squared, right, which is exactly the same. But now we have a negative root, which means this becomes root of a negative of minus 1, which is complex term j. Right? S equals minus zeta omega n plus or minus j, that j coming from this negative because I flipped the zeta of minus 1, root 1 minus zeta squared. What's that telling us? So now, if I go on to the next slide, this is the function. We've got a real part here and imaginary part here. So we can plot these roots on the root locus. Right? So if I just, and we remember that for the Argand diagram, we always plot x plus yi, right? So in this case, x is minus zeta omega n, y is plus or minus, because we've got 2 roots, plus or minus omega n, 1 minus zeta squared. So if I put an x, and I've got my complex conjugate here, so I know that this real part, this is minus zeta omega n, and on the imaginary, we've got omega n root 1 minus zeta squared, and minus omega n root 1 minus zeta squared. Right, so that's the location of our roots, our closed loop roots, for our standard second order transfer function. So now what we've done is we've related the closed loop root location on the S-plane to the natural frequency and damping ratio of our system. And we can go a bit further. So we can find, let's call that h. So we know h squared equals the square of the 2 sides. Now this side is zeta omega n. This side is omega n 1 minus zeta. So this is by Pythag. The other side, so the hypotenuse squared equals so adjacent over opposite, adjacent squared over opposite squared. If we multiply this out, this is going to, negative is going to cancel because it squares out. Right? But so it becomes omega n squared. Then the square root is squared, giving us 1 minus zeta squared. Okay, so that equals zeta squared omega n squared plus omega n squared plus minus omega n squared plus times zeta squared. just multiplying out this bracket here. And then these two cancel. Just leaves us with omega n squared implies our hypotenuse h equals omega n. Right, so we can now replace our h and say this here is omega n, our natural frequency. So the natural frequency of the system where it has a closed loop root or a root at a specific location on the S-plane is given by the distance from the origin to that pole, that root. So what else can we find out from this simple plot? Well, we can also say that if we have some angle here, we call this gamma, then the cosine of this gamma is going to be minus zeta omega n, and we just determined that our adjacent is omega n. These cancel. So cosine of our angle equals zeta. So if we want to find the damping ratio of our system, we can take the inverse cosine of the angle from the real axis in a positive, taking starting from the real axis and going in this time in a clockwise direction. If we take the angle, and then we take the cosine of that angle, that will give us a corresponding damping ratio. So now, these two characteristics by which we are describing our second order system, which are our natural frequency and our damping ratio. And if we have our damping ratio and our natural frequency for our system, we can predict the time response because we have a set of second order systems data that does that for us. And these values here, zeta, because 1, 0.8, 0.6, 0.5, these are our damping ratio, and it's normalized in terms of omega n. So if you know your omega n and you know what your damping ratio is, you can sort of get a pretty good estimate just from this set of second order systems data what the time response is going to look like, what your time to peak overshoot is going to be, what the magnitude of your overshoot is going to be. This is all system step response data. I should have mentioned that again or reminded you, but this is step response data, right? So we're looking at step response. You could kind of estimate what the settling time is as well. So I'm just trying to tie everything together here for you because you can see now why the root locus allows us to sort of short circuit our path to get the time response of our system, because we can now, based on the location of a root, we can now get omega n, we can get zeta, therefore we can get the second order system's response. If we make that assumption that this is a system which is dominated by a pair of closed loop roots which are closer to the imaginary axis than the other roots, right? Let's look at how we value or determine the gain k that corresponds to any point on our root locus. That's what we want to do now. Any location of our closed loop roots, we want to determine what's the value of our gain k for that particular location or that particular set of closed loop roots that we have. And for this, we start from our characteristic equation, come back to this 1 plus kgh equals 0. So we can get an expression for k, and the magnitude of k is taken by taking the modulus of that expression. So all we've done here, of course, is we said k, well, okay, we just rearrange this. So take a minus 1, or 1 across to this side, make it minus 1 divided by gh. All right, and then we're taking the modulus of that. If we have an open loop transfer function that has the form like this, where we've got a set of zeros and a set of poles, right, then we can assume unity feedback. So assuming h equals 1, then k is basically, or the modulus of k, the value of k equals 1 upon g. Right, so we just, the modulus of 1 upon g. So we're just flipping this equation. So all the poles come on the numerator, all the zeros go on the denominator, and then we're taking the modulus of it. And to take the modulus of the overall equation, instead of taking the whole thing, we're taking the modulus of each term. So the modulus is the magnitude, right? So we're taking the magnitude of each of these poles and zeros. What's the magnitude? Right, the magnitude is the, any number, any, let's say, value on an Argand diagram is defined by, its argument theta and its magnitude x bar, right? So any imaginary number has a magnitude and an argument. So what we're doing is just taking the magnitude of each of the zeros and the magnitude of each of the poles and multiplying them up to get the value of k. So all the poles, take the magnitude of each one by one, multiply them together. For all the zeros, take the magnitude of each, multiply them together. But what we're doing is taking the magnitude from some location S. So if I have a root locus that looks like this, right, say let's just use the same one that we had before, right? So plot the real axis, and then we've got a breakout point, and then the locus is going off like this. Okay, so this is my imaginary and real. So let me take some location, some closed loop root on this. So we're going to say our closed loop roots are at this point on the locus. Each, there'll be a closed loop root on each locus. So there are 3 closed loop roots, but these 2 that are close to the imaginary axis, these dominate the response. So I'm really interested in the magnitude of these primarily, but so what I'm interested in now is the magnitude, the value of the distance from this closed loop root to this pole, and this pole. So if we say we call this P1, P2, and P3, and we're going to call this location on the root locus, this closed loop root Q. So what we're really interested in is the distance between Q and P1. That's, if we call SQ, then we're interested in the magnitude or the distance from Q to P1, Q to P2, Q to P3. So for instance, if P1 equals 0 and Q, I'm just going to make up a number here. Let's say it's 0.4 plus 2j, right? That's the location of this closed loop root Q. So the magnitude of Q plus P1 is going to be the square root of 0 squared and 0.4 plus 2j squared. Okay, so because just get it using Pythag, and that gives you this distance from P1 to Q. All right, so that's going to give us, I don't know, these are going to cancel, and well, anyway, I'm not calculating it out, but that's how you do it, right? That's how you do it. So you just take the Pythag. So this is the same actually. So you can say the magnitude of Q P1 is actually the magnitude of Q times P1. It's the distance between the two. So we're finding K for some value of S equals alpha plus I plus J beta. So we want to say what K gives us Q. What value of gain? So remember, our gain will start at 0 at the poles, and it will increase as gain increases in our system. Then our closed loop roots are going to move from our poles towards a 0 and infinity. So as we increase gain, we're moving along this locus, and then we're going to depart at some point when gain gets high enough. We're going to depart from the real axis. We're going to become oscillatory. So now our system's got some oscillation in its response, and then it gets up to eventually to this point Q. We're asking what value of gain gives us this point Q, and that's what we can get from this equation, this analysis here. So let's look at an example for this. If we take this system, so we've got a fairly complex plant model here. It's a fourth order. You know, you could by just looking by observation, you can see, okay, this is a complex root here, a complex pole. So we've got poles at 0, -4, and this is going to be yes. Well, we use a quadratic expression for this, equals what was it again? Plus b. Okay, it's trying to help me out. Equals minus b plus or minus root b squared minus 4ac over 2a. Right. So we're using this quadratic expression to find the roots of that part, and that will be complex. Right? So we can determine our poles. We also have, in this case, a 0. Right? So we know, again by observation, we have 1, 2, 3, 4 poles and 1 0. So that means that one of our loci is going to start from one of these poles and it's going to end up at the 0. The other 3 loci, which start from the other 3 poles, are going to go off to infinity. So we're going to have 3 asymptotes because we've got 3 poles that are producing loci that can't go to zeros. So we're going to have 3 asymptotes. So using all of that information, we can plot the root locus. And the question is saying, well, can you tell me what the value of gain k is that gives an overshoot of 40%? So how do we get that? Well, first of all, as I said, we have to get our poles and our zeros. And our poles are at 0, -1, and well, this is the answer to what I was alluding to earlier, which is -2.5 plus well, 1.94j, and then the fourth pole -2.5 minus 1.94j. Right, and then we've got this 0 and -5. So to get 40% overshoot from the root locus plot, we need to find the dominant second order equivalent poles that lie at what? Because remember the question we just looked at was saying plot the root locus and then determine the gain that gives this overshoot of 40%. So from 40%, that is MP, our peak overshoot, equals 40%. And we have to go and find out, well, what damping ratio is going to give us an overshoot of 40%. We can actually use our second order systems data to get an idea, or we can use our equations from transient response lecture to get a more precise calculation. So we're going to get our damping ratio zeta. And in fact, when you look into it and find out what damping ratio from a second order system gives 40% overshoot, the damping ratio is about 0.23, right? So we're going to have a second order, we're looking for a second order, a dominant pair of second order closed loop roots that lie at a damping ratio of 0.23. That's going to give us an angle based on what we looked at here. This angle gamma corresponds directly to our damping ratio. So if we have a damping ratio of 0.23, to get our angle gamma, you take the inverse cosine of the damping ratio of 0.23, and that gives us a gamma of 76.7 degrees. Then based on that, we can get a location on the root locus. So we can do it graphically. If we have some point Q on the S-plane, and Q is the closed loop pole or the closed loop root location, then if we can measure the distance to each of our poles, P1, P2, P3, and Z, then as long as, and this is a graphical method, if you're drawing this, plotting the root locus by hand on graph paper, as long as your scale is the same. So every time you plot a root locus on graph paper, when you're asked to plot the root locus, try to make sure you have the same scale on your imaginary and your real axis, because that will make these graphical methods a lot easier. If you have different scales, even measuring an angle to get the damping ratio, you're going to be off. So make sure, that's why I've underlined and highlighted or in bold this statement. Make sure that your root locus diagram has both axes are drawn to the same scale, the imaginary and real axis to the same scale. Then you can literally just measure with the ruler the distance between Q, P1, P2, and Z, right? They can be measured. Don't forget to apply the scaling factor. If you're using, say, one gradation to 1 centimeter graph paper, but you're plotting 2 gradations per value of your S-plane, then you have to remember that you have to, if you measure distance, you have to divide that distance by 2, right? Because otherwise you end up with the wrong scaling. If you've plotted your locus carefully on graph paper and you have scales that match, then you can literally just measure the distance between your closed loop root Q, which you found because it's where the locus crosses a given damping line, and you want that damping to give the response you want to get, the time response from your system. Right? If you do that, then you can literally just measure from Q to P1, Q to P2, Q to P3. Those are distances in centimeters now. Make sure that you scale it based on the scaling of your diagram, your root locus plot. Divide it by the distance between Q and Z, and that will give you the value of K. Now, let's come to this system. This is probably a bit more complex than anything you'll get in your exams and so on, but it's worthwhile for demonstration purposes for this particular thing. So what we see here is let's identify our poles and zeros of this system. These are them, and we can see that P1 comes from this term here. P2 is a real pole. This is our open loop poles and zeros. It comes from this term. P3 and 4, complex poles. They come from this term here. And then the 0 comes from the numerator, this term here. Okay, so that's where our poles and zeros come from on this system. And if we wanted to now, plot this system, we would be faced with a problem, because we can easily draw the location of P1, P2, and Z1. We can draw the location of P3 and P4, but we don't know where the locus that emerges from these two poles, the loci, two loci, one from each pole, we don't know how they emerge. So if we wanted to plot the locus, then we'd have a bit of a problem. So in some circumstances, the open loop system has complex poles. And in order to sketch the root locus for the closed loop system, we need to determine the angle of emergence of the locus from those complex poles. All right, so you can see an example here. We have a complex pole here. This is it right here. Right, and we want to know, well, at what angle does the locus emerge from this complex pole? And that angle being theta. And the angle of emergence can be determined by using something called the angle condition. Right, so this is another condition that we apply when we're dealing with root locus, which allows us to determine this particular characteristic. So this is the important concept. This is the angle condition here. if a point lies on the root locus, the argument of that point will be a multiple of 180 degrees. So any point, any closed loop root that lies on the locus, if you take the argument of that particular closed loop root, then you'll find it has to have a multiple of 180 degrees. Right, so here's an example to make it, hopefully try to clarify what I mean by that. This is our closed loop root Q. If this point Q lies on the locus, so it's drawn as lying on the locus, right? If it's going to lie on the locus, then the argument of Q has to be a multiple of 180 degrees. It doesn't have to be 180 degrees, just has to be a multiple. So 180, 360, what comes after that? 540, 720, etc. Right? So it has to be a multiple of 180 degrees. So the argument, so what's the argument? Well, the argument of Q is going to be basically the sum of each of the angles from the other poles to that closed loop root. Right, so we have 3 poles here, each with an angle between the real axis and that particular closed loop root. So P1 has angle P1, P2 has angle P2, P3 has angle P3. And what we're saying is that the sum of all those angles has to be a multiple of 180. Now, in fact, the argument, remember that Q, represents a point on this locus. It represents a point on the S-plane, and there's a transfer function associated with that. So, because poles are on the denominator of the transfer function, and the angles associated with those poles are actually going to be negative. So, all the poles are added up in a negative a negative sign, and they have to be a multiple of 180. If there's a 0 in the transfer function, that's going to be a positive angle. Right? So here we have a transfer function with a 0 at 2. We've got P1, P2, and P3 here. These are the 3 poles. So if we were to take the argument of this, we're going to take the argument of this transfer function, then what we would do is we would say, well, that is the argument of S plus 2 minus the sum of the arguments of all your poles, right? So it's going to be minus the argument of S plus P1 minus the argument of S plus P2 minus the argument of S plus P3. Right? That's how you're going to find the argument. So the argument again is the angle between a location, a pole or a 0, and a specified position identified as being the closed loop root. So the sum of all the zeros, the angles from all the zeros, minus the sum of all the arguments of all the poles, has to be a multiple of 180. And this just shows, 180, and this little term here allows you to calculate multiples. So let's look at a little example here. If we take an open loop transfer function with 4 poles, right? So we've got pole P1, pole P2 here, minus 1, but then we have 2 complex poles, P3 and P4. Right, so we have 4 poles. Now, in order to determine, remember what we're trying to do, we're using the angle condition to determine the angle of emergence of the locus from a complex pole. So if we select a point that's just infinitesimally to the right of one of those complex poles, like the one that's flashing on the screen here, then well, but we're saying it's close enough that the angle between that point on the root locus, the complex pole, sorry, beg your pardon, the closed loop root and that pole P3 can be assumed to be 0, right? So we're just kind of infinitesimally edging out, and we're assuming the angle is 0, and we're going to now measure or calculate the other angles, right? So we're going to calculate all the ones that are circled now, P1, P2, and P4, the angle between each of those poles and that closed loop root that's just snuck out of P3, an infinitesimal amount. Right, so here are the pole locations. P1 is -10, P2 is at -1, P3 is at -4 plus 4j, P4 -4 minus 4j. Right, so the first angle phi1, which is here, is going to be, we're just using tangents, pretty straightforward trig. Opposite over adjacent, opposite is 4, adjacent is 6. Right, so that gives us 33.7 degrees for phi1, which looks about right, visually. For phi2, the angle now is going to be from the positive real axis in an anti-clockwise direction. So this is the angle. This is confusing in as much as it's the opposite angle to the one we use to calculate our our damping lines, which I mentioned at the beginning. So now we're taking our positive angle in the opposite direction. And then this one, P4 is a complex conjugate of P3. That means the angle from P4 to the closed loop root, that's an infinitesimal smidgen away from P3. That one is going to be 90 degrees because it's the complex conjugate. So that one's pretty obvious. Don't have to calculate anything there. Okay, so now we're going to apply the angle condition, which says that the sum of all these angles has to add up to a multiple of 180 degrees. So if we add these angles, we actually have an unknown. The unknown is what's the angle of, between the closed loop root position and P3. We've assumed it's just moved an infinitesimal distance away from P3. We assume the angle is 0, but now we can say, well, we don't actually know what the angle is. So we're going to take the angle as an unknown, and that's the only unknown now in this little equation. So we're going to set n equals 1, or n equals 0 rather, so we're just saying 180 equals the negative sum of the angles of each of those poles, right? The argument of each of those poles. So that's minus 33.7, minus the 126.9, minus 90, right? So all of these, and then minus some unknown, which is phi3. Right, so this is how we can now calculate phi3 by rearranging all of this. We get that phi3 is minus 430.6, which of course is the same as minus 70.6, and this is degrees. Right, so the actual angle of emergence from phi3, if we now say it's no longer infinitesimal, we're moving a little bit away from P3 with our closed loop root along the root locus. That means the root locus has to emerge at an angle something like this, right? This is about minus 70.6 degrees. It's minus because a positive angle would be from the real axis or the horizontal in a counterclockwise direction. Okay, Ernell, you're asking what n represents in this equation. N is just like we did for when we looked at the angle of the asymptotes. We had that same factor, it's just an integer number, and it scales from 0, 1, 2, 3, 4. So it's an integer counter, if you like. And we can set it, basically you're setting it
to 0 for the sake of this calculation. But mathematically, this equation would be satisfied for any integer value of n. Right? So as you climb up through the values of n, you continue to satisfy this. Now think about it, 2n plus 1 means you're always going to have, if n is greater than 0, you're going to have an odd number here. Right? So if n is 1, you've got 3. So it's 3 times 180. And that is the same as 180 because 3 times 180 is 540. You've basically gone round the circle and come back. The next value, 5 times 180, would be 1,420, right? I think, and that was also another multiple, right, of 5 to 10. Sorry, no. It would be actually 900 and be 900. Yeah. So every time you go around the circle, it kind of ching ching ching. It holds true. All right. So all n is an integer value, or an integer counter. But what that allows me to do here is, instead of saying phi is 400 minus 430.6 degrees, we could apply that and say, well, that's the same as 70.6 degrees. Okay. So this allows me now to actually draw on this locus or on this plot where I put the poles before. Let me just go back. So before I just had the poles. Now I can start to draw my locus, because I can use the real axis rule coming from the left-hand real axis. Every time you touch or intersect with a pole or a 0, you toggle the locus. So over here there's no locus. When I get to P2, I turn it on. There's locus all here till I get to P1, then it turns off. Right? So we know we've got a locus between P1 and P2. What else do we know? We have 4 poles and no zeros. So that means we're going to have 4 loci, and each loci is going to go off to infinity at some angle, right? And basically, if you have 4 loci going to infinity, you're going to kind of divide the circle into 4, and you say they're going to go off at 45 degrees, 135, 2, what is it going to be? 235, and 315. I think those are the 4 angles. So basically, the asymptotes are going to be evenly distributed around 360 degrees. And so that's what we expect here. So I've just sketched on where the loci would lie, starting with the real axis rule. And now, critically, I have the information I need to be able to calculate the angle with which this complex, this closed loop root emerges from the complex pole, and where it goes from there. So it's coming out at minus 70, but then we know it's going to swing because it's going off up at 45 degrees, because we've got 4 loci going off to infinity. So each of those is going to be, evenly distributed around the circle. And this one is going to be, this is maybe, that's 180, and 45 is 225. And this one, the asymptote, this one's going off at all the way around here. This will be 315 degrees, right? So these asymptotes, and they're all coming from a center point, which I haven't drawn on here. The center point would be somewhere here. We can calculate that based on the rule we got before. How do you calculate the center of the asymptotes? Right, so you've got these 4 asymptotes coming off at 45, 135. Right, so anyway, get rid of all that. Okay, so now the most important thing is we've calculated the angle of emergence. That's what we're trying to calculate, and we're now able to sketch how the loci is proceeds from there and converges to its asymptote. Now we only calculated for one angle of emergence, but the other one is going to be the complex conjugate, so this is going to be basically minus 70.6 degrees, because, oh, beg your pardon, this is minus, so this is going to be plus 70.6 degrees, because it's the complex conjugate. You're always going to have to match. So you only have to calculate one angle of emergence that will tell you what its complex conjugate is going to be as well. Okay, so now we move on to our next example. And this is the same open loop transfer function that we had before, but I've added a 0. So look here, this size is a 0 at -1, and I've shifted, this is a pole before, I've shifted the pole to the origin. Okay, so now these are my poles and my zeros. The poles are at 0 and -10, 0, -10, and then we've still got our complex conjugate pair, P3 and P4 at -4 plus or -4, but now I've got a 0 at -1. Okay, so how does this change things? So the only thing, two things change. One is the pole moved from -1 to 0, and then we introduce the 0 at -1. So we can still use our angle condition. We still want to determine what's the angle of emergence of the closed loop root from this pole P3, which will give us the complex conjugate for P4 as well. So we're going to make the same assumption that our closed loop root is infinitesimally away from P3, and we're assuming the angle is 0. So now we can calculate the angle from each of our poles to that closed loop root, and now also from our 0 to that closed loop root. So these are the new values. Angle phi1 is slightly different because it's in a slightly different place. I think it is. Yeah, it was 126.9 before, and now it's gone to 135. Right. Phi2 is unchanged because that's still in the relatively the same position as it was before. Phi4, that's the complex conjugate, so it's always going to be -90, the angle measured like this, of course, right? Or 90 degrees, sorry, not -90. But now we have our 0. So our 0 is going to basically be the same angle that our pole was before, which is it's going to be, sorry, 126.9 degrees. So the big difference now is that our angle condition has a 0 to take into account. So we're still using the same angle condition, 180 times a multiplying factor equals the sum of the zeros minus the sum of the poles. The sum of the argument of the zeros minus the sum of the argument of the poles. So now we will be applying that, and this is our 0, that's a positive number, and then all the others are negatives. Right, these are negatives. And then we're also going to have a negative phi3, which is our unknown. So again, we have phi3 as our unknown. We can rearrange to get the expression in terms of phi3. The answer we get is minus 311.8. So now, what's the angle? It's coming out at, this is the negative direction, because for this positive, clockwise is, counterclockwise is positive. So this is minus 311.8 degrees, which is the same as plus 48 degrees. So the angle of emergence now is shifted because we've got this 0, introduced this 0. It's going to change the way the loci look, right? We've got this angle of emergence of 48 degrees now. So I've sketched on here again. This is what our new locus will look like. Now we have a 0. That means that we have 3 asymptotes instead of 4. Because one of our poles, the locus that emerges from one of our poles, is just going to end up at the 0. And it's a very short little bit here, right? The locus that comes out of this pole P1 is just going to go straight to this 0. Then we're going to get, have no locus, and then when we get to P2, we'll pick up another locus on the real axis going off to minus infinity. And then we just calculated that our angle of emergence here is our 48 degrees. And now these loci are going to go off to, instead of plus or minus 45 degrees, these are going off to plus or minus 60 degrees. So the asymptote looks something like this. Okay, and this locus is really supposed to converge to that asymptote. Remember, we learned before how to calculate the center of the asymptotes and the angle of the asymptotes. How did I calculate the angle from the zero? Ziad is asking. The angle for the zero is calculated in exactly the same way as the angle for the poles is calculated. So we're assuming that we have this closed loop root that's basically at the pole, but it's just a smidgen, an infinitesimal distance away from that pole P3. So to calculate the angle or the argument of the zero, then you would just use tangent. So the angle, well, if I calculate this angle, the internal angle, call this, I don't know, gamma, because that's so confusing. Let me see, I'm going to call it delta, just for the argument's sake, haha, argument, too much use of the word argument. Right, so we call that delta, then delta equals tan to the minus 1 of opposite, which is 4 over adjacent, which is 3. And that will be what is it? That's 53 degrees. Or 63. 60, I think. Right. So delta's so it's 63 degrees, and what we really want is this angle here. This is the theta Z1. It's going to be 180 minus 63, which is 127, I think. All right, so that's how we got angle theta Z1. Okay. Okay, so now we apply the angle condition again, but now we actually have a value for this 0. Well, okay, I did that already. Yeah, got that 48 degrees, and then we plotted. Right. All right, so moving on to a 3-pole example now. We have 3 poles and no zeros, so we're going to have 3 loci that go to infinity along asymptotes. If it's 3 poles and no zeros, then basically the asymptotes, you're going to have 3 asymptotes, and those asymptotes are going to be evenly distributed. So if you divide 360 by 3, you get 120. So they're going to be 120 degrees apart, and so there's going to be one going off at 60 degrees, one going off at minus 60 degrees, and one going off at 180 degrees. Right, so these are our asymptotes. We can calculate the location of the center of the asymptotes by using the equation I gave you for that earlier, when I say earlier, in the previous lecture. Right, that's the center of the asymptotes is the sum of the poles minus the sum of the zeros divided by the number of asymptotes, which is the number of poles minus the number of zeros. Right. That one I gave you a couple of classes ago, I think. All right, so that will give you the center of the asymptotes, the location on the real axis from which those asymptotes emerge. All right, so what we're doing is we're saying what's theta 2? or phi 2, the angle of emergence of this locus, this closed loop root, from P2, our second pole. So we could state our pole positions 0, -4 plus or minus 4j, right? So we've taken off the pole which was at -10 before. So now our phi 1 is going to be 135. It was the same value as it was before. Phi 3 is 90 degrees, same as it was before. And then if we apply our angle condition, there's no zero. There's no zero. We've got P1, P2, and this is the unknown is phi P3. So theta P3, sorry. So our 180 is going to be minus our P1, which is our phi 1, which is 135, minus phi 3, which is 90, minus our unknown phi 2. So now our phi 2 is going to be minus 45. So that means it's coming out at this angle. Right, because for this, the positive direction is in the counterclockwise direction. Right, so we calculated the angle of emergence for this one. So now we can plot our loci. We know we've got 3 asymptotes. So our 3 loci going off at 60, minus 60, and 180. We calculated that before, and now we know that the loci emerges at minus 45 degrees from P2 and plus 45 degrees from from the P3 at the bottom. All right, so we're dealing with an excuse me. We're dealing here with another system, and this one has a mass spring damper with hydraulic actuator. So what are our poles here? Well, we have a pure integrator here. That gives us a position of P3 equals 0. And then the roots of this are complex. And that gives us our complex conjugates, P1 and P2, minus 1 plus or minus 2j. So if I was to sketch the root locus, it looks like this. Is actually almost the same as this one, right? Positions will be a bit different, that's all. Right, so now we're trying to find the angle of emergence from P1, which is phi P1, shown on the diagram, just above Q. Right, so Q is, we're assuming it's shown a good distance from P1, but we're assuming it's infinitesimally close or infinitesimally away from P1. So if we assume that, then, based on what we've just done in the last couple of examples, we calculate the angles. Phi P2 is going to be 90 because it's the complex conjugate. That's this one here. Again, it doesn't look like 90, but this is just exaggerated for illustrative purposes. Right? And then phi P3, that's this one here, this angle, is going to be, using our tangent rule, 180 minus inverse tan 2 upon 1, so 117 degrees, right? So just slightly more than our 90 degrees. And then applying our angle condition, we get this. It gives us minus 27 degrees angle of emergence. So it's going to come out somewhere like this. All right. So we're looking at minus 27 degrees here. All right. So I'll just ask the question here: what will the center and angle of the asymptotes be? And the center of the asymptotes is going to be the sum of all your poles minus the sum of all your zeros divided by n minus m. N is the number of poles, m is the number of zeros. So you have one asymptote for every locus that doesn't end up in 0. That's what this n minus m means. So in this case, you've got -1 plus 2j plus -1 minus 2j plus 0, right? And no zeros, so nothing to subtract. Now, when you have complex poles, your conjugates will always cancel off. So only the real part comes into play here. And then you've got 3 asymptotes that divide by 3. So this is going to be -2 upon 3 for the center of the asymptotes. So that's going to be about here somewhere. Right? And then in terms of the angle of the asymptotes, then that's given by a multiple of 180 divided by the number of asymptotes. There are 3 asymptotes, so we're dividing our circle by 3. Right. So the angle of the asymptotes is going to be it's going to be 60 degrees. It's going to be, next one will be at 180, and the third one is going to be at 300 degrees, right? So that's the values of k equals 0, k equals 1, k equals 2. Okay, so that's just let's try to kind of keep closing and coming back to what we looked at before. So this is our resulting root locus plot. And, oh, okay, I did it on the next page here. This is the center of the asymptotes, -2/3. And this is the angle of the asymptotes, pi by 3, which is 60, pi, which is 180, 5 pi by 3, which is our 300 degrees. So. All right, so let's look at well, this is continuing with looking at a sort of mass spring damper system, but now we've added, I think, compared to what we had before. Well, we're just generalizing it compared to what we had before, right? So before we had specific numbers for our mass spring damper part of our model here, and now we're just generalizing it. So if we're looking at an underdamped system where zeta is less than 1, as we vary a value of k, our controller k, right, then what's going to happen to our pole set? Well, remember that our poles, our closed loop roots, start at our poles and move along the loci, either to infinity or towards a 0. Right, so when we have a low value of k, we're going to have pole set A. Pole set A showing that all these closed loop roots are close to the poles. Right, so these are the closed loop roots of the characteristic equation. The loci, the root locus, is the movement of the closed loop roots as some parameter in your system changes. The parameter that's changing is gain k. So we're starting with a k of 0, and that's where, and at that point, the closed loop roots will be at the poles. As you start to increase k from 0, then the closed loop roots will start to move away from the poles along the loci. So if we sort of fast forward, and we've now increased gain k to a point where we have pole set B. This pair of complex conjugates, this complex conjugate pair of closed loop roots, is going to be, they're moving along the loci towards the imaginary axis, but this real pole this real closed loop root is moving away from the imaginary axis along this locus as k increases. So is the second order approximation valid when we have a low value of gain? Well, not really. So for pole set A, you can see that the root which is closer to the imaginary axis is this one. If this is closest to the imaginary axis, say it's at minus 0.5, right? So this closed loop root is going to correspond to a term in our output e to the, say beta t, and sorry, let me draw this in a slightly better place. Our output function, a constant plus a set of exponential terms, right? And remember the coefficient or the power of the exponential is the closed loop root locations, right? That's the roots of the characteristic equation. So for pole set A, if this pair corresponds to beta and delta, you can see that the real part is going to be, so let's say this is minus 3, right? So the real part beta is going to have an imaginary part as well, which causes oscillation, but the real part is going to be, say, minus 3 for gamma, and then delta might be minus 0.5. Now minus 3 is going to decay a lot more quickly than minus 0.5, so the response of pole set A is going to be dominated by the real root, which is the closest to the imaginary axis. When we increase gain and we move this complex, the closed loop roots closer to the complex ones closer to the imaginary axis and the real one further away from the imaginary axis, then what's going to happen is that this pair of roots is going to have a smaller real part. That means it's decaying more slowly. So in our response function, beta and gamma are going to have a smaller real part. They're going to hang around for longer. But this real root on the real axis, this one here, this one is going to decay, right, much more quickly. So this one is going to have, let's say that's delta, it's going to have a larger real part, and it's going to decay more quickly. Right, so as our gain increases, as we get this pair of closed loop roots here closer to the imaginary axis, this is a third order system, but we can now approximate it to a second order system because that pair of closed loop roots is dominating the response and it's closest to the imaginary axis. So the second order approximation becomes valid when we have some higher level of gain k.
So this kind of starts to whet our appetite in terms of control system design, right? And goes a little bit beyond just being able to plot a response or change the gain. This starts to look at how can you actually change the characteristics of the response of a system, which translates into being able to modify the shape of the root locus. So if we consider a basic system like this, to plot the root locus, we can go through the normal process. Like, so what's the location of the closed loop roots, for instance? We can see straight away that our closed loop roots are going to be at s equals 0 and at s equals minus 1. Are there any zeros? There are none, right? So 2 poles, no zeros. You know where our poles are. We've got our location of our, well, let's say open loop poles. You've got that so far, right? Then we could determine the location of our closed loop roots. How can we do that? Well, we could take the closed loop transfer function. So C S over RS is going to be forward path over 1 plus open loop. right? So when we multiply that out, that'll give us 10 over s squared plus s plus 10, right? So now this is our closed loop transfer function, so the roots of this give us our closed loop root CLR, which is this. Okay, so we can get our closed loop roots, and then we can calculate the damping ratio. So what are our closed loop roots in this case? And I did not calculate this earlier, which I should have done, so I'm going to have to use s equals minus 1 plus or minus root 1 squared minus 4 times 1 times 10 all over 2 times 1. Okay, so that's going to give us minus 1 upon 2, a complex, plus or minus j, well, it's going to be 40 minus 1, which is root 39 upon 2. Okay, so that's going to be our closed loop root positions. So we got that bit. All right, so I'm just going through partly to revise how we do all this stuff and go through the various steps of plotting a root locus. So our closed loop roots are going to be at s equals minus 1 upon 2 plus or minus j 3.12. Right, so that's our closed loop root location. So therefore we can calculate the damping ratio, and the damping ratio on our closed loop roots, if I just sketch over here, use a bit of space and sketch the locus. We know we're going to have a locus between these two. Maybe I should use a different color. All right. On the real axis, it's going to be between the poles, because if you come from the right hand side and track towards the left, when you intersect with a pole or 0, you either turn the locus on or off. So there's no locus on this part. When you get to the pole at 0, the locus on the real axis is going to be active until you get to the next pole, which is now going to turn it back off. So that's it. And then we're basically going to have a breakpoint of a half, and that you can see that just simply by the geometry of the system, and the loci are going to go off at plus or minus 90 degrees. Right, so I'm just quickly calculating, determining what the locus looks like, and then we just said, okay, the closed loop roots are at minus a half, plus or minus 3.12. So that's this location here. So that's going to be on a damping line. The damping line comes from the origin, pass through that point, through that closed loop root. So what's the damping ratio of this particular point? Well, you have to get that by calculating first of all the angle. And so alpha equals the inverse tan of opposite over adjacent, 80.9 degrees. So gamma equals 80.9 degrees. So this is a very large angle, which means it's going to be a very low damping ratio. Zeta is equal to cosine of gamma, which is about right, what we'd expect, 0.16. Okay, so we've got our location of our closed loop roots, we've got our damping ratio. How do we get our damped natural frequency? Well, the damped natural frequency is the distance of this line from the origin to the closed loop roots. So that's just by trigonometry. So omega equals the square root of 0.5 squared and 3.12 squared by Pythag, right? So omega n, if you look back up further in our notes on closed loop roots, then the distance omega n, the natural frequency, well, this is technically the damped natural frequency. Should do this, call this omega d actually. So omega d, our damped natural frequency is going to be that distance from the origin to the closed loop root. Right, from the origin here to the closed loop root. So that's simply calculated by Pythag. The root is the hypotenuse, so it's the root of the sum of the squares. So that's what we get for this one. So it's 3.15 I have for that. And that would be in radians per second, right? So have we got our damped natural frequency? Yep. Next, static velocity error constant. We'll skip over that one, but in the interest of time. But what if you wanted a damping ratio of 0.5 and a natural frequency of 3 radians per second? Well, what would you have to do to get a damping ratio of 0.5? If we come back from here, you have to take inverse cos of 0.5. Right, so from here, you take the specification here, damping ratio of 0.5, and take the inverse cos of it. That's 60 degrees, right? So gamma has to now be 60 degrees. So I'm going to do this in blue. So our angle has to be 60 degrees for our damping line. That means the angle is coming out like this. Right, let's see. So the blue line is, we're calling this zeta equals 0.5. Of course, this is just a sketch, so very approximate. That's our damping ratio of 0.5 damping line. Now, our damped natural frequency of 3 radians per second means that this distance here from our closed loop root has to lie on this damping line, and it has to lie 3, the value of 3 from the origin. So this is the location. Now, if we just calculate what the real value of that is, let's call that x. So we can do that again using cosine. So cosine of the angle equals adjacent over hypotenuse, x over, we said that has to be 3 radians per second, okay? And the angle is 60 degrees, we said, right? Angle is 60, so that means 3 cos 60 equals x, and that's 1.5, right? Or minus 1.5 j in this case. So, I beg your pardon, minus 1.5 is the real. So the problem is now that location is all out over here. So we've now calculated the actual closed loop root location we need is right here. I'm having a problem doing a dot. Right, every time I do a dot, it comes up with a menu. Right, so this is really where the closed loop root location is. And of course, that's not, so this is where we need to be. We're off the locus. So we can't get to this location just by adjusting our gain. When we adjust our gain on this system, all that will happen is our closed loop roots will move from the poles along the locus and off towards plus or minus infinity at a real value of minus a half, right? So there's nothing we can do really by adjusting our gain to get us to this point here, which is where we want to be now. This location in space, if you like, in the S-plane, is the location at which we would have the required damping ratio and damped natural frequency, right? So this is not achievable with the current locus. So what we have to do is actually adjust the shape of the locus. You have to adjust the shape of the locus so the locus now passes through this point Now, how do we do that? We can do that, obviously we can't do it just by changing the gain, but we can do it if we add poles or zeros. So you can introduce something called a compensator. A compensator is what allows you to put in these additional poles and zeros. And with the CISO tool, you can actually add poles and zeros manually. Using CISO tool, you can add different types of poles and zeros. You can add a real pole or a real zero, or you could add a complex conjugate pole or a complex conjugate zero. So you can now add these different elements using that same root locus plot, and that causes the locus to change shape. So that allows us to now get the response we require. So if we can change the shape of the locus, then we can get it to go through this point that we're trying to get to go through. If we can bend it backwards, for instance, we could get the locus to go through this point, and then we could adjust the gain so that the closed loop roots come and land right on this point. We say, okay, that's the gain we want. You know, we could put in a pole or a zero, and that gives us the response we want. Right, so you can induce this thing called a compensator, additional poles or zeros. So that's why our controller is not GC because it's G controller. It's usually GC because it's G compensator. Right, that's what we normally use as our nomenclature for our compensator. Right, so this is what we can do. So we need to now design what GC is, design our compensator to give a modified, or to modify the root locus and give the desired closed loop root pole, closed loop root position, which we just specified there. Right, request to go back over that again. So you see this scribble here and now? Is this making sense, or is this where you're confused? You understood what I did here? On this slide, I was just answering a set of questions for this particular system, a basic system, right? And I went through item by item to answer what's the location of the closed loop roots with the system as it stands right now. So as the system stands, what's the damping ratio? I showed that the damping ratio is based on the calculations I did here, based on the location of these closed loop roots. I was able to say, well, then I know my damping ratio is going to be, first of all, I've calculated my angle of the damping line, and then based on which I did using tangent rule, and then using the cosine rule, I can calculate my zeta, my damping ratio, because zeta equals cosine of this angle gamma, right? So now I've got the damping line, it goes through the closed loop root location. I've calculated my damping ratio. The third thing is what's the damped natural frequency, and we said, okay, damped natural frequency is the distance from the origin to the closed loop root, and that damped natural frequency then can be calculated using Pythag. And again, it all comes from the closed loop root location. The closed loop root location is -1/2 plus 3.12j, right? So now I calculate my omega d using Pythag. Then I skipped this one, and then I came to the last one and said, well, okay, I've got my damping ratio and my damped natural frequency, but now I'm being given specifications for this system. I want this system to have a damping ratio of 0.5, and I want it to have, let's say, a damped natural frequency, and I'm going to change this to omega d to make things a little easier. Omega d, a damped natural frequency of 0.3 radians per second. Right, so those criteria actually specify a damping line angle, and the angle of the damping line to get 0.5 damping is 60 degrees. Why? It's the inverse cosine of 0.5, because zeta equals cosine of the angle, the included angle here. right? So if we take zeta is 0.5 and we find the angle gamma, that's now giving us an angle of 60 degrees. Right, so the blue line is the new damping line. I want my closed loop root to lie on this damping line so that it has a damping ratio of 0.5. But I also want it to be 3 radians per second natural frequency, omega d. And so I can calculate, well, I could either measure, if I plotted this, measure 3 along the line, that's going to give me omega d from the origin along this damping line. Or I can do it using a simple bit of trigonometry and say, well, if the hypotenuse along this triangle is 3, then I can calculate my my side opposite, adjacent to the angle rather, right? Because I know this is 60 degrees inside here. Hypotenuse is 3. So 3 cos 60 is going to give me this distance here along the real axis. So the location of this closed loop root to give me a damping ratio of 0.5, a damp natural frequency of 3 is going to be at a real value of minus 1.5, right? So 1.5 is this dimension here. Now, as we can see, this closed loop root is not on our green line, which is the locus for this particular system. That's a problem. So we can't get our closed loop root to this point, because the only way we can move in the S plane, is really by changing the gain in our system. As we change the gain, we can move our closed loop roots along the loci from the poles to the zeros or off to infinity. But this point is off the loci, so what can we do? Well, what we have to do is take an approach whereby we modify the shape of this loci so it can pass through this point. That's what I want to do. I know what my design point is, like this is where I need my design to be. So the question now is, how do I change the shape of my locus? Right, so that's what we're coming to now. How do you change the shape of your locus? Well, you do it by using a compensator, and a compensator allows you to add poles or zeros. So we have to design a compensator, GC, that allows our closed loop roots, or the locus now, to pass through this desired closed loop root position, through this blue X here, that we identified as being where we want to be with our closed loop roots. So we're going to do it by having a compensator. So I've genericized the example we just used. And instead of 1, I've just got an A here. So this is a first order type 1 system. It has 2 poles, one on the origin from this pole and another pole at minus A. Right? And now we're going to go through a process of, well, this is the locus that we'd have for this simple system. 2 poles, no zeros. If you have 2 poles and no zeros, then you're going to have 2 asymptotes going off to infinity. If you have 2 asymptotes, then they're going to be, basically, to determine the angle of the asymptotes, you have to divide your circle by the number of asymptotes. So the circle is 360 degrees, divide that by 2. So the asymptotes are going to be 180 degrees apart. And the first one's going to be at 90 degrees, the next one's at 270. So that's how we end up with this cross-like shape. So the red line now is our locus, the x's are our poles from this simple function. Right, next, let's move on to the next slide. So we're going to modify this now, we're going to change the shape of it. Right, so the first thing I'm going to do, these are my original poles here, 1, 2. Now I'm going to add a pole at minus B right here. Right, so the original shape of the locus, of course, is this here. But now I've added B. What have I done? Well, the locus shape has changed because now I've got 3 poles and no zeros. So I'm going to have 3 asymptotes, 3 loci going off to infinity. Now if I have 3 going off to infinity, then they're going to be 120 degrees apart, because it's 360 divided by 3, so they're going to be 120 degrees apart. I can calculate the center of my asymptotes and draw lines to show where they're going, and we know the loci are going to converge to those asymptotes. One of them is going to be along the negative real axis, the others are going to be at plus or minus 60 degrees, right? So you can see how I've changed it from this original line. I could probably draw that in green or something just to highlight it. So I initially had this green dotted locus. Now what I've done is I've added this minus b as an additional pole. Let me say I've added another pole at minus b, and that's caused me now to have 3 asymptotes instead of 2, so the shape of the locus changes. I've got one closed loop root that's going off here on this locus, and I've got a complex conjugate pair going off on this pair of loci. Now, okay, so we have this setup for this first modification of adding a pole at minus b. But what I'm going to do now is I'm going to actually add another pole, and this one's going to be at minus c. So remember, we originally started with these 2 poles, the one at the origin and minus a, but we've since added b, and now we're adding c as well, a pole at minus c. So what's going to happen now? Well, now you've got 4 poles and no zeros, so you're going to have 4 asymptotes. So your asymptotes are going to go off at 90 degrees apart. The first one's going to be at 45 degrees. Oops. The second one is going to be at 135. The third one is going to be at 225, and the fourth one is going to be at 315. Right. So those are the angle of the asymptotes. You can calculate the center of the asymptotes, plot those asymptotic lines. All the asymptotes emerge from one single point. So again, we've changed the shape of the locus. You can see, compared to the previous one that we just did with 3 poles, has actually caused, this is the 3-pole locus here. It's actually caused this locus to move in this direction. Okay, so for the same gain, say, if you have a closed loop root here or here, this complex conjugate pair, then you're going to have a corresponding complex conjugate pair on this side. But these ones are going to be most important. These are the more important ones here. And these are the dominant ones because they're closest to the imaginary axis. This pair's got a larger sort of negative real component, so they're going to decay a lot more quickly. These ones are going to hang around longer. So the ones on this side closest to the imaginary axis are the more important ones. And you could also see that compared to where the closed loop roots were before, on this green loci, by adding the additional pole and pulling the loci to around a bit, pulling it this way a bit, it's actually caused probably an increase in the damping ratio. Certainly the locus, the closed loop root is closer to the imaginary axis, so it's going to have a longer decay time. So it might have to take longer for any oscillation in that response to settle if we're applying a step input. Right, so there's a few comments around that. Now what we're going to do, instead of adding those 2 minus b and minus c poles on the real axis, we're just going to add a complex conjugate pair. So I've eliminated b and c, and now I'm adding a complex conjugate pair, which is here. All right, so that's our new pair. Oops. And well, the locus, I didn't draw it in red here. The locus, of course, will come here. So it's 4 poles and 4 asymptotes again, because there are no zeros. So we still have the same
4 poles and 4 zeros. You've got asymptotes going off at the same angles, which is going to be 45, 135, 225, 315. So those are the angle of the asymptotes. We can find the center of our asymptotes is going to be somewhere around here. These are asymptotic lines sketched roughly. Right. 4 poles, no zeros, 4 asymptotes. They're evenly distributed around the circle basically. But the difference now, of course, is that these are complex. So it effectively changes the way in which the system, the closed loop roots will move. They're going to be a bit further away. You're going to have an oscillation component to the closed loop roots that's on these loci. But still, the ones on these pair of loci here, which is the closest to the imaginary axis, these are still going to be the dominant poles, closed loop roots rather, and dominate the response of the system. What we've done with this one is, of course, we've added, we've got rid of our complex conjugate closed loop poles, and now we've added a real zero at minus B. This one's always a fun one. So now we've got our original pair of poles at 0 and minus A, and now we've added a 0 at minus B. So now our n minus m equals 1. Right, so we only have one asymptote. Our n is the number of poles, m is the number of zeros. Now we have 2 poles and 1 0, so we have one asymptote. If we have one asymptote, it's going to be heading out at minus 180 degrees, right? Or 180 degrees, let's say, as you start measuring the negative counterclockwise direction for the asymptotes. Right, so now we have this one locus going off to minus infinity along the real axis. But the other loci, so there are 2 emerging from this pair of poles. One comes around the top, the other goes around the bottom. One goes out to minus infinity, the other comes in and arrives at the 0 in the middle. So that's the dynamic now. Now this one has some hope for us, because if you remember, if I just sort of estimate where we had our closed loop roots, we said before, in the example I was looking at the start, we said originally, I don't know what's going on with this. Right, originally we had our closed loop roots like here and here. And we said, well, we really want our new closed loop root to be somewhere around here. So you can see we're on the right track here. If we change the dimension of the circle by maybe moving this 0 in or out, then we could actually get the circle to pass through this location. Right? Not by doing that, but probably by shifting it out a bit, increasing its diameter, right? Something like that. Sorry about the bad sketch there. Right, so we could actually adjust the location of B in and out, and we could get this locus to pass through this point, I think. So this might be part of our answer. Put a 0 in place, and then we should be able to get something close to what we want. Another thing you could do, and this one could also work for the situation we're looking at, is you could actually add a complex 0. So that means you have a complex conjugate pair of zeros. How do you do this? Well, in this case, your GCS would be something like AS squared and BS and C over 1, right? So this is a could give you a complex pair of roots, which is your complex 0, right? So that would end up being 0 with a real part and an imaginary part. So what's happening here is both these loci emerging from these 2 poles, one's going up here, the other's going down here, they both converge to, each one converges at a 0. There are no leftovers, so there are no loci going off to infinity in any direction. Right. One last one, we got here a
a real pole and a real zero. So our controller in this case would be S plus C over S plus B. Right, that's the controller we have here, and or our compensator rather. So this is a very common type of compensator. This is called a lead lag, or it could be a lag lead, depending on whether C is bigger or B is bigger. Right, but this one in this case is a lead lag because B is a smaller number, C is a bigger number. That means B is more significant than C. So this is called a lead lag compensator, and you can see the pole and zero added here. What does this do? Well, it kind of pulls. Remember, this is originally vertical, and now it's pulled this locus in this direction. And again, by adjusting B and C, you can get more movement on this. Right, you can get this locus to kind of come around a bit more. What's going to actually happen is eventually it's actually going to go back vertical. Why? Because you have three poles and one zero. So n minus m, 3 poles minus 1 equals 2. So you have 2 asymptotes. If you have 2 asymptotes, then your asymptotes are going to be 180 degrees apart. They're going to be a plus or minus 90. So the asymptotes are still the asymptotes are still at plus or minus 90. Right? That's the asymptote there. So this locus is going to converge to the asymptote as I showed it. Right, this is the asymptote. So it's converging, but it's sort of bending around as it does that. And as you move this zero outwards, or adjust the location of this pole, you can move the asymptote, the center of the asymptotes. And as you move that center of the asymptotes, this locus is going to change shape, so it could go further this way or whatever. And that allows you potentially, again, this is another potential solution because we've got a point here we want to pass through. So we could adjust the location of our B and our C, our additional compensator pole and our compensator zero, to change the shape of this locus and to get it to pass through this point that we're trying to get it to go through, to give us that damping ratio and natural frequency that we want our system to have. Here is an extract from Ogata, our course text, one of our course texts, showing a lot of different formats or forms of loci with different types of poles and zeros. So with this one we're familiar with. This is our basic 3-pole, no zeros. And you could also have 3 poles but a complex conjugate pair. The asymptotes are going to be the same. They're still going off at plus minus 60 degrees and minus 180, but the shape of the loci is a bit different. This one, you have a pair of real poles and you have a complex conjugate pair of imaginary poles. You've got 4 poles, no zeros, so you've got 4 loci going off at 90 degrees to each other, right? Right. This one, 4 poles, no zeros, so but now you've got 2 sets of complex conjugate pairs for your poles, and so on and so forth. So each of these you can kind of see the logic and the shape of the loci. So you basically always know, you can very quickly estimate or get a sense of the shape of the loci that you're going to be generating.